my translator.
No, it's directly plugged into the laptop. So. Yeah. Okay. So we are going to continue on. The stream going out that is being recorded looks nice. So the rest of us, we're going to suck it up and just listen to what we are here to learn from Holger Vogt. So please give a round of welcome to Holger.
Yeah. Okay. So many thanks. NGspice circuit simulator in pink. Talk about standalone and embedded into KiCad. Well, I'll give a short introduction to circuit simulator. Then talk about what's new in NGspice. Talk about the KiCad NGspice interface. And give some simulation examples. Well, conclude with what is next. Yeah, why circuit simulation? You emulate electronic circuits per software. It should be cost efficient and time saving. I think that's it. Yeah. Some details, of course, you can check functionality without making hardware. It's very important if you do IC design, because fabricating an IC with a defect circuit, this is very expensive. You can check for parasitic elements. You can make variants very easily, change some device parameters and see what is happening. You can evaluate new concepts with not too large an effort. You can cross-check against automatic circuit generation as a final simulation test. You can anticipate reliability, make degradation simulations. And it's a good learning experience because you can look into a circuit without using hardware to do so. You can see voltages and currents in different branches, and this is very interesting. Yeah, NGspice, what is it? It's a circuit simulator that numerically solves equations describing electronic circuits. It can also be other types of circuits, for example, thermal, could also be mechanical. And you are interested mostly in time-varying signals. And in electronics, it's current and voltages. It's the open source successor of the venerable SPICE 3 from Berkeley. Okay, we have a circuit. This is a very simple circuit, an inverter with 2 transistors. And this is the entry to NGspice. So NGspice is a command line input tool. Many people said, woo, command line. But I've just learned command line is very nice. KiCad has got a command line and other software also, so we are not too bad with that. Okay, you have the net list, the SPICE net list, which contains circuit description, power supplies, transistors, some simulation commands to run the thing, and some model data to run this thing. The output is graphical indeed. It's a time axis and the voltage axis. The ideal green input, yeah, it's green still. And the simulated output, you see the inverted signal. Yeah. This is the NGspice user interface. Yeah. On the input side, you put in the circuit netlist, the circuit description. You put in models or model parameters for the devices you're using in your circuit. And you put in simulation commands. And the output could be data tables or tables to file, of course. Could be graphical plots. We use the venerable X11 interface or native Windows plotting capability. Or you can plot to PostScript, SVG, or you can use GNUplot or other tools for outputting. Yeah, what's new in NGspice? The current release is NGspice 42, released in December 27th last year. We have an additional matrix solver. I will talk about these things a little bit more in detail in the following. We have a new matrix solver in addition to the venerable spares 1.3. We support Verilog-A coded compact device models. We allow co-simulation for mixed signal simulation with Verilog digital circuit blocks and mixed signal digital analog parts within NGspice. We allow co-simulation, again mixed signal with C-coded digital, so there is a way to translate C code into NGspice readable shared libraries. And we have, and I'm benefiting from the vastly improved graphical user interface KiCad, especially the upcoming KiCad A is offering for using NGspice. Well, the matrix solver. What is the circuit simulator doing? The circuit simulator, if you look inside, NGspice gets the circuit, makes a setup, parsing the netlist, reading the model files, and then it is, if you do a transient simulation versus time, then you have the ever circle here between model equation evaluation and these data go into the matrix, and the matrix is solved, and then you go for the next time step and you repeat this until the time is over, and you look at the output. The model evaluation is already running in parallel in NGspice. We use OpenMP, so if you have a multi-core processor you typically have today, you use benefit from that. The matrix evaluation is not parallelized. These sparse matrix solvers are difficult to parallelize. So we had been looking for a long time for an additional matrix solver. Use the spares 1.3, developed in 1986. And now we use, in addition, optional selectable KLU matrix solver, which is ongoing development by T.A. Davis and his co-workers. And with KLU, you get a speed up of simulation by a factor 1.5 to 3 if you have large circuits, and especially if you do circuits for IC simulation. And this is, of course, an advancement. We allow Verilog-A compact device models in NGspice. Compact device models, these are the model equations describing modern transistors, for example. These complex, tiny things like FinFETs or so would have 500 parameters and lots of differential equations to describe, and people do the development in Verilog-A. And so we had a real need to have an interface to this Verilog-A, because this provides access to the modern devices like BSIM bulk, which is for ultra short channels, or BSIM CMG, which is for FinFET, or for gallium nitride devices, power devices, high-speed bipolar transistors, and so on and so on. Yeah, and we got this set up in cooperation with the company Semimod, who did this open source development. We have the Verilog-A model description. We compile this model with the open source compiler OpenWAV, compile it directly into a shared library, and this shared library can be read by NGspice, which has got the OSDI interface. So we are reading directly the Verilog-A compiled model from a shared library, or DLL. Yeah, we make use of this. For example, had been mentioned maybe already, open source PDKs for IC design are upcoming, and one of these is the IHP open source PDK. And this is a 130 nanometer CMOS process with integrated ultra-fast bipolar transistors. Ultra-fast means 500 gigahertz or so. The model used for the bipolar is the so-called phobic model, which is integrated into NGspice for some years now. And the MOS model is a PSP model developed by, currently I think, developed by Leti in France. And this is Verilog-A. And we translate this, put this into NGspice, and so we can support this open source PDK with simulation. And this is just a simple example, 19-stage NAND gate ring oscillator. So we have 19 NAND gates in series, feed them back, and it starts to oscillate. And we have a frequency. This is an FFT of this signal, a frequency of 600 megahertz, and you divide it by 19 by 2, and then you get an inverter delay of 280 picoseconds. Okay. Yeah, we allow digital Verilog circuit blocks into NGspice. Looks a little bit more complex, but isn't that much complex. We have a Verilog digital circuit block. We compile this with open source compiler Verilator into some intermediate C code. And then we compile this intermediate C code with some C templates in addition, which are constant, always the same. We compile it with GCC or MSVC into a C-coded shared library. And this C-coded shared library is read by NGspice. NGspice has a so-called code model interface, and we have written a code model decosim which directly interfaces this shared library. So we can now run simulation with this standard NGspice netlists, which may contain lots of analog plus digital blocks. This is an example. It's just a demo. It's not productive simulation. This is a successive approximation register analog to digital converter, 6-bit. And this uses the digital SAR block written in Verilog with the analog part, which is a capacitor array with some switches. Okay, and even if things look complex, using this is not very complex. You need 2 commands. Yeah? You have this command NGspice, and NGspice calls a script written in NGspice control language, and you enter the ADC Verilog description. It compiles the Verilator thing, it compiles the GCC thing, and then you call the Spice netlist with the standard command NGspice ADC.sir, which contains the analog part and contains the simulation control, and then you get this kind of thing. Okay, I just have enlarged a little bit. You see that the successive approximation. This is a new, this is the ramped in voltage. And this is, the x-axis is time. And this is a new start. You try to get the value of this point here. It starts with the starting value and then successively approximates the input. Well, with a certain delay, 8.5 microseconds here, which is the time you need for the conversion. Then you are here in the stable phase, and this is the red line, just shifted by 8.5 microseconds, is, well, the output signal. Yeah, so digital plus analog. Okay, you can also do this with C-coded digital type of models. You have C-coded independent processes. You compile them with GCC, for example, or with any C compiler. And these communicate with NGspice via another code model. The digital interface is now called dprocess. Well, this has been developed by Juros Platise from Isotel some time ago, but we have now, for the recent version, have adapted it a little bit, modified it, so it will also run under MS Windows. And now we can, simulate some circuit which has some circuit blocks from C code. This is just, again, an example, a simple example. The C code you see here, this is a gray code generator. This gray code generator is compiled and loaded into NGspice, and this is the output. The output plotting here is by GTK wave, because this is a nice digital plot. Yeah, and you can use these kinds of blocks. So you define these compute function with data out and data in and some other, and the time or the clock circuit, clock going in, and then you can run C-code digital circuit. Okay, so I want to talk about schematic entry for NGspice, because this is under continuous development, and yeah, it's a nice usable thing. Why do we want to have such a graphical user interface? Well, netlist as input quickly becomes confusing. You need schematic entry. You need to see schematics, and then have an interface to the simulator. You can get better documentation, of course, if you group inputs and outputs. And this is not an NGspice development. So we developers for NGspice don't develop these graphical user interfaces. We make use of existing ones or support their development. And of course you need one because all other simulators, or most of all other simulators have one. Yeah, so you have to offer one. There are 3 of these interfaces currently under development where we cooperate. This is a thing called XSchem, whose main focus is on IC design. There is another one, QXS. This is a very universal interface and specializes a little bit in RF simulation. And then, okay, we have the KiCad. So I wouldn't say that KiCad is developed because it's a graphical user interface of NGspice. No, the other way around. Yeah, you have heard about this PCB design and layout tool, and it offers simulation, and the simulation engine is NGspice to support the circuit designer. And of course, I can then make use of this beautiful interface. Okay, just show these interfaces in strange colors. Yeah, I won't talk about these. I want to talk about this one, again in strange colors. Okay, but you could imagine that it could look nice. This is the schema window with some simple circuit, a simple phase shift oscillator with a 4.2 kilohertz frequency oscillating, and down here you see the FFT. Of course, you see it's not a super clean sinusoidal signal, but okay, this is the 4 kilohertz thing here. Yeah, so what is the interface looking like? It's eSchema does this schematic entry. eSchema generates the SPICE netlist, and eSchema also does a graphical presentation of the results. So it sends the circuit netlist to NGspice, it sends model parameters to NGspice, so the simulation commands, and it gets back simulation results. And NGspice is here used as a shared library to this KiCad process. Yeah, I would like to make a live demo. I don't like these colors, but let's see if we can survive somehow. Okay, this is my starting template. I do not start with from this 0 because it takes too much time. So this should become an operational amplifier. Simple thing, amplifying by a factor of 10. Okay, what is missing is the operational amplifier. I try to grab it from the library. So we just load the library. It takes a little bit of time, but only once the first time, and then it gets faster. I know that it is in the library simulation SPICE, and here's the op amp. I grab it and I move it, and hopefully it fits, because yeah, it did last time? Yeah, it does. Okay, so this is how you place additional elements. Very simple. But now let's stop. We don't need any more, I hope. Yeah, and now we do simulation. This is a real-time simulation. I look inspect for simulator, and I get this simulator interface. Well, black is green and pink is white. Okay, I'm sorry for that. What do we want to do? We want to do the transient simulation. Transient simulation is output versus input versus time. Okay, and so we have, what is our input? Let's go back and have a look. The input is a sinusoidal signal with an amplitude of 0.1 volt and a frequency of 1 kilohertz. Okay, back to the simulator window, and I just click onto Start Simulation, and here's our simulation. The input is the small one, and the output is the red. Stays red. That's great. Is the red signal. Okay, so this is transient simulation versus time. We could have another simulation. To be honest, I've prepared this for. This is so-called AC simulation, small signal simulation versus frequency. So you see the frequency behavior of this kind of circuit. We again run the analysis, and you see that the amplification is 20 dB, so it's 10, is constant, but the operational amplifier has one single internal pole, and so it goes down. Okay, so this is very quickly, you just see what's going on. I think I have time to make some additional change. I put an additional capacitor in here. I collect my capacitor, I transform it because I have to rotate it. I put it just in here. Let's do it in here. And I have to give it a value. I guess I take 1 micron. Yeah, and then we go back and do the AC simulation again. Oops, there's something changed. We have this is sort of low pass behavior. It stayed, and now we have some high pass behavior for the low frequencies due to this input capacitor. Yeah, so very quickly you do a small change, and with a simple click, we are there. Okay, so this is what I wanted to show live. Let's go back to the slides, and I give some more examples. Yeah, the first example, this is, again, why do you want to simulate? This is a 2.5 kilowatt Class D audio amplifier. And you would say, well, this is strange. No, you go to some Amazon and click in looking for these kind of amplifiers, and for $300 you can get a kilowatt amplifier today, because it's a digital amplifier. Yeah. And okay, so what did I do to get this simulation? Okay, I made a symbol myself of this audio driver circuit, just drawing the symbol. And this audio driver circuit is also something I created myself, because it has the analog input, it has a pulse width modulator. This is a translation from the analog signal to a pulse width digital signal. It needs something more. It needs a complementary push-pull output, because we have 2 transistors here. And it has a dead time generator to avoid shoot-through, because what will happen? You have minus 100 volt here, plus 100 volt here, and if you manage to open both of these transistors at the same time, you will see the result in form of smoke. And so you have to avoid this. Okay, and some simulation commands in here. The input is 2 volts, again 1 kilohertz. And you see the power supply. The output load is a 2 ohm resistor. Well, and this is the output. This is the input signal, and this one is the output signal, okay? And with the double frequency, you have the power signal, the blue one here. And if you do an RMS over this output power signal, you see here it's kilowatt up to 4.3, for example, you will get an output power of 2.6 kilowatt. The simulation has a great advantage. Nothing explodes. You can just do it, and if you do, you can investigate the output filters and can check loudspeaker models and everything just by simulation. Of course, you can also do real-time or real amplifiers. This is Tiberio Vicol has made this Q17 amplifier derived from the famous Quad 405 audiophile amplifier. You see lots of transistors in this thing. The output stage, the input is an operational amplifier. This is the modern contribution of the whole thing, and some voltage generators here. Well, yeah, and you can of course simulate this and looks similar to our 2.6 kilowatt. It's 100 watt, and what you see here is just at 300 milliseconds we switch the output load from 8 to 7 ohms automatically, just to check what the output load would mean, and you see a little bit increase in output power. Yeah, and so you can model all these things and model the influences and so on and so on. Okay. NGspice allows to do mixed signal simulation. Mixed signal simulation means you have analog and digital circuits in the same simulator. And you could also simulate the digital part like the analog part, but this takes a lot of time. And if you have more than a few gates, it would be much too slow. So NGspice includes in the so-called event-based simulation, which is very fast. And this is a mixture. Well, this is the venerable 7400 series of devices. You have flip-flops here. You have some output decoders and some NAND gates, and you have some XOR. Oh, no, this is NOR gates. Yeah, and you can simulate this whole thing together. And you see that this is mixed signal means because we're using the digital output here for a delay line. Yeah, so we have an RC delay and another RC delay, and we have the original signal, and so this gives an output pulse of a specific width. And this is a clock signal generated in this circuit. And this circuit here, which is shown, is a rotary encoder. So an encoder which does give optical signals when it's turned around the one or the other way. And this is the digital output, again plotted with GTK wave. And you see this here, the Q1 signal is coming before Q2 signal. And because in the rotary decoder, these two decoders are shifted a little bit, so you know that this is turning left, for example. And here, the turning is changed to the other direction, and you see the Q1 is coming later than Q2. And this is detected by this circuit. So you have here the pulses, or let's say for turning left, and then left turning, switched right turning, and then you see the output pulses here for the turning right. Yeah, so mixed signal simulation is, and this is effective because the whole simulation thing is 25 milliseconds. So it's ultra fast. It's a click and it's there. You can even run this on this computer here, which is not the fastest machine. Yeah, and we can have pure digital. I made a symbol for this up and down counter. You have the input clock, you have the input up and down signal, and you have, so it's an a 3-bit 8-state counter. And inside of this is a state machine, and it's a very, very simple state machine. You have here the states from 0 to 7, so the 8 states. Here are the signals. You see from 000 up to 111. And here is what the states are switching. The input is at 0 state, and if the input is 0, input means backward counting, then the next state is this one here. Or if the input is 1 and we are at state 0, then we go to state 1. If we are at state 1 and we count down, we go back to state 0. If we are at state 1 and we count forward, we go to state 2. So you can do very simple programming inside one of these code models used by the digital event simulator of NGspice. Well, and here's just the signal, the clock signal. This is the up and down signal, and we count up, and then we switch to down, and then we count down, and we switch up again. Yeah, so very simple simulation, and the simulation time of this whole thing is a mere 37 milliseconds, so it's very fast. Okay, so much about the examples we have. What's next in NGspice? Here are listed some ideas, some more or less fixed plans, and some actual activities. We will do more tests with the open source PDKs. We supporting the Skywater PDK and especially the upcoming IHP PDK to support analog, mixed signal, and RF simulation to support these kind of designs. We will improve the RF capability by adding harmonic balance with a special effective method, for example, to simulate intermodulation of signals and so on. We will support reliability and degradation simulation. Well, nothing lasts forever. Chips don't last forever. And people sometimes want to know how long they will live. And so you can try to model that. And this will be done here. And hopefully with a funded project. This is very, very interesting. Yeah. There has been the request for transient noise simulation. This is a difficult task. Because we don't want to rewrite the complete simulator. We have to figure out ways. And again, here it would be, if somebody is interested in integrating this into NGspice, please let me know. We will improve the usability of KiCad NGspice graphics interface. There's continuously people are requesting things, and we are detecting things, and we can try to simplify things. We can try to support more of what NGspice is offering internally right now. For example, the digital simulation is should be supported by having digital basic blocks as input and digital plotting, for example, as output. And we have to enhance compatibility because, well, the world is, somehow we are competing against commercial simulators like LTSpice or QSpice or PSpice and HSpice and whatever. We cannot do this in full, but the basic things should be compatible. But all these four I have mentioned have slightly different input languages, slightly different models. And so you have to take care of this somehow. Yeah, that's it, what I wanted to provide you with information. Here is some support websites if you need more details. Here they are. Thank you.
So while we are taking questions, the video team is going to try to repair the video locally. So your questions will not be able to refer to the slide.
Hi, Holger. You said something about degradation of semiconductor devices. Would it be possible to simulate the degradation based on radioactivity?
Yes. This is included in this development plans.
Thank you for the presentation. A quick question is, how do we input the state machine in the component? Is there a special window where we come and we type it, or the state machine must be written in a .c or .something and we give it to the component?
Yeah, the simple state machine, the question is, how can we code the state machine into NGspice? The simple state machine I've shown is just a text file. This text file is loaded. You put into your Spice netlist a single line with a specific model, and this model loads the state machine. That's it for these simple things. The complex, yeah, you could, of course, write state machines in C code if you want to. Then you have to do this translation.
My question is maybe a bit naive, but would it be at some point feasible to include the tracks or geometry inputs from KiCad in order to mimic the links that you place between your Spice components?
Please, it's a little bit
track width, and we also have like the PCB stack-up. Would it be somewhat feasible to, from these geometry inputs, associate a kind of approximation of the S parameters of each lines between the components?
Yes, there is some work ongoing. It's not that intensive to use an EM solver. It's called Sparse Lizard, to extract these data from your lines in KiCad. Yeah, I think it's a lack of manpower to make this a real tool. Yeah. KiCad has added IBIS simulation, so you have IC output and IC input. Only the output and input signals, and many semiconductor vendors offer these models. And then you could basically have a transmission line or an RC line in between to simulate the signal integrity. The problem is, as you said, to get these data from your PCB. Slowly moving on. Basically, yes. But this is a KiCad or is schema work. It's a KiCad work. It's not the NGspice. The NGspice takes the transmission line parameters or takes the parasitic capacitance, the resistances, and then does the simulation.
The EM would have to be dealt from KiCad.
Yes, exactly. The EM has to come from KiCad.
I wanted to ask if anybody has used the C interface to, for example, make simulations of existing microcontrollers or things like that you could have in your design.
Yeah, there has been some activity on this, very scarce. I think it's two. It's Joris Platise from Isotel. You just look up his website, Isotel, then you could find some information on that. There has been another guy, I think he has used Arduino interfacing to NGspice, but I don't know much about these work.
Are there any dynamic languages that are possible to be used as a model, or is it just compiled languages that have to be loaded? If you don't care about simulation time, for example, would it be possible to use any scripting language to?
Yeah, there are various kinds of making models. You have the Verilog-A road, but this is compiled and static. Yeah, when it's compiled, it's there. You can do models with NGspice internal nonlinear voltage sources, for example, and these are very dynamic. Yeah. And many power semiconductor device makers, they make so-called sub-circuit models, which are comprised of SPICE commands. And these can be very complex, difficult to debug, but then you can do whatever you could imagine.
Is it possible to perform simulations over PVT, so over process variance and voltage variance?
Yes.
Right. And would it be possible to do this without changing any of the models itself? Like, can you just plug in a model?
This is the typical content of modern semiconductor PDKs when you think about IC simulation. The worst case simulation or corner simulation is typically integrated. It's different model parameters. The model stays the same, but certain parameters are changed.
So we have a question from online. Just heads up, we're still working on the video, so lucky for us, Holger is able to continue answering questions for the foreseeable future. Online, they are asking, is there any post-processing of waveforms such as THD, FFT, etc. possible?
FFT is standard. FFT is standard in NGspice and is standard in the KiCad NGspice interface right now. It's more or less 2 clicks and then you have it. Yeah. You can set up, NGspice has a very powerful scripting language. Well, another language. It's not Python, it's another language which originated in 1990. So, well, we keep it up and have now more than 100 commands available. And you can do a lot of data processing with this scripting. So, for example, classification into bins, or if you do Monte Carlo, you can run Monte Carlo simulation. You can classify these data into bins. You can do a lot of post-processing internally in NGspice. Well, of course, if this is not enough or you want to use standard interfaces, there are Python NGspice interfaces available. So you can use all these Python libraries which are there for data processing. So it's a lot of action, but the action has to be done by you.
Okay, we have time for one more question.
We do not actually work time.
Okay, so let's give Holger a round of applause. Thank you very much. Okay, so we're going to check